We're still right on time, 2:40. So our next presenter is Chris Ogren. He's a fourth-year student, also from the University of Michigan, and he's going to talk up to us about calibration for a large gadolinium-doped water Cherenkov detector. So please, Chris.
All right, thank you, Sean, for the introduction. As you just said, good afternoon, everyone. I'm going to take a few minutes to talk to you about some of the recent work we've done at University of Michigan in the development of nitrogen 16 and 17 calibration source for large gadolinium-doped water Cherenkov detectors. So antineutrino measurements are useful tools for remote monitoring of nuclear reactors. There's a couple scenarios in which this applies. One would be the discovery of undeclared nuclear reactors. Another would be monitoring operation of known nuclear reactors, such as I think the example has been given of Hartlepool or other reactors that have multiple cores or multiple reactors operating. You could tell when one is on and one is off, both on different kind of operational characteristics such as that. The advantage of using antineutrino measurements is that the signal essentially cannot be shielded, and using the right detector, you can detect the signal at long standoff distances in the order of 10 to hundreds of kilometers. This is relevant to the NNSA mission of non-proliferation because it enables verification methods for declared reactor sites and their operational schedules and characteristics. It allows for discovery of undeclared reactor sites, and it gives an indication of departure from declared operational characteristics. For example, if there were to be an undeclared shutdown that would be used to remove or repurpose partially spent fuel for the production of weapons material, that would be something that you could potentially see in the overall rate of antineutrinos that you were monitoring. Large water Cherenkov detectors, especially those that are gadolinium-doped water, are promising for remote antineutrino detection. Currently, these are under consideration as part of the Watchman collaboration and NE0. As many presenters have already gone over, antineutrinos can be detected through inverse beta decay events where an antineutrino recoils off of a proton, which gives you a positron and a neutron. And in gadolinium-doped water, that positron gives you Cherenkov light if it has high enough energy, and the neutrons are captured by the gadolinium dopant, which releases a number of high-energy gamma rays in a cascade, which can then go on to create Cherenkov light by interaction scattering off of electrons in the water volume. Under Watchman, the scale of detector that we're looking at is kiloton scale, so a very large amount of water, and that amount of volume gives you the ability to account for the low interaction cross-section of antineutrinos and the long distance away from the reactors potentially, and the kind of 1/r² rate losses that you could see from that. Additionally, what's under consideration is building these large detectors underground where they can be shielded from cosmogenic background radiation, which can interfere with the kind of low signal that you would expect to see. So calibration of these gadolinium-doped water Cherenkov detectors requires a variety of sources. The neutron capture gamma ray cascade from gadolinium has a very wide energy range, all the way up to about 8 MeV in terms of gamma rays. So you need a number of neutron sources to calibrate your detector response at various points along that. Currently, the sources that are under consideration are thallium-208, which gives you about 2.6 MeV gamma ray, americium beryllium, which gives you 4.4 MeV from the excited state of carbon, and nitrogen 16, which gives you 6.1 MeV gamma ray, which is near the high end of the gamma ray cascade continuum. The neutron sources that are also under consideration for looking at your efficiency of capture with the gadolinium dopants and so forth is the americium beryllium source that I mentioned. And then another potential source that we're looking into is nitrogen 17, which is a delayed neutron precursor. So nitrogen 16 is the source that we've mainly been focusing on in the work done at Michigan. It's useful because it emits a beta before the neutron, so it's time taggable if you're able to detect that beta particle. But it also decays very quickly. It has a half-life of about 7 seconds, right? So there needs to be some sort of mechanism to both produce this source and then transfer it into a useful area where you can use it to calibrate your detector. And so the design that we're looking at is based on what's already been done at the Sudbury Neutrino Observatory, which uses a gas volume of CO2 that's irradiated with 14.1 MeV neutrons from a DT generator to produce nitrogen 16 through the NP reaction. And then that nitrogen 16 containing gas is transferred into a small decay chamber volume that can be placed inside of the water of the actual detector, where the nitrogen 17 then decays and releases the gamma rays. So part of the MTV impact of this project, the development of this nitrogen 16 calibration source is kind of a two-university project between the University of Michigan, where we were mostly working on source generation tests and the characterization of the production and kind of the spectral results that we see out of that, but also in collaboration with the University of Sheffield in the UK. They have some more infrastructure in terms of building the physical prototyping of the delivery system, and then they'll be able to perform kind of the actual tests once that prototype is in place. They have a large water tank and kind of the systems that are required to do that. So moving back to what we've done at Michigan in terms of nitrogen-16, we've done some initial production tests and modeling of our detector response to those high energy gamma rays. We've just done some simple demonstration experiments with a DT generator and different targets, a bucket of water, a tank of CO2 gas, and then we use a large sodium iodide blade detector to measure the gamma rays that come out of that. And in the spectrum that you see on the left, you can see, we can very clearly see the features that come out of nitrogen-16. The 6.1 MeV photopeak, as well as the single and double escape peaks. And to a lesser extent, you can also see the less probable 7.1 MeV branch, which is also one of the decay branches from nitrogen-16. And then if we move to the top right plot, this is a bin from about 5 to 6.1 MeV on the spectrum on the left. And then just looking at the time behavior, the decay over time of the events in that energy region, and you can see that the temporal profile matches what we expect based off of the known decay constant for nitrogen-16. And then on the bottom right is just a comparison of the observed light output spectrum in sodium iodide compared to our simulated model of just the 6.1 MeV gamma ray. And we can see that we're able to get pretty good agreement between our laboratory measurement and our simulations. So another thing that we're looking at University of Michigan is the potential of nitrogen-17 as a possible calibration source. Nitrogen-17 has a discrete delayed neutron energy spectrum, and those delayed neutrons are correlated with beta emission from the nitrogen-17, which gives you a time taggable, discrete energy, low energy neutron source. And the main advantage of developing the source alongside the nitrogen-16 is that both of these isotopes can be delivered by the same physical delivery system. And the only change that you would need to make is swapping out the target material for CO2 or something that's enriched in oxygen-17, and then it uses that same NP reaction to produce the isotope. And so our goal moving forward at Michigan is to demonstrate a proof of concept of using this source, which we're going to do with a slightly more advantageous or higher cross-section, higher density target of oxygen-17 enriched water. And so you might be asking, why nitrogen-17? Why is this useful? We already have a calibration source that's being looked at for Watchman in americium beryllium. Well, one of the things about nitrogen-17 is that not only does it offer a different energy range in terms of neutron interactions, but also has different tagging systematics in terms of the ultimate decay chamber that you would place inside the detector. So for americium beryllium, you have a decay unit that has a tagging detector to provide time tags on those 4.4 MeV gamma rays that then give you kind of a start time for when the neutron is emitted. But what can happen is when the neutrons are then captured in the gadolinium in the water, the gadolinium gamma ray cascade can actually trigger the tagging detector inside of the americium beryllium source. And if you don't get enough Cherenkov light from the other gamma rays produced by the gadolinium capture, that can lead to a false tag where you have a time tag, but then you don't get a response in your detector, and the time tag is not associated with the initial 4.4 MeV gamma ray. So nitrogen-17 could be used as kind of a cross-check and a validation with these two sources together, because it has different tagging systematics, much less likelihood of gadolinium capture cascades then causing tags if you use a thin scintillator that's only designed to measure the beta particles coming out of nitrogen-17. So just moving into kind of what we have designed for our work at University of Michigan going forward and our proof of concept. Our plan is to use a small vessel of enriched water, oxygen-17 enriched of about 2 grams, and then we'll irradiate that with our DT generator and measure the spectrum that comes out of it. Eventually, the idea is to enclose that with a kind of structure with thin layers of scintillator that can then be used to provide the time tag for those neutrons, and then we can validate kind of the expected production rate and the ability to use the time tag with the neutron spectrum. And then just some Geont 4 simulations that we've done show the expected energy of the beta particles escaping from the water from both nitrogen-16 and 17, and then the expected energy deposition in those thin scintillators surrounding the vessel. And based on the amount of energy that we see in simulation being deposited, we're optimistic that we're going to be able to see those tags when we get into the laboratory. So next steps moving forward, is just simply the measurement and validation of nitrogen 17, excuse me, production. We have a suite of specialized neutron detectors available to us at University of Michigan for conducting tagged, beta tag neutron spectral measurements. Among those, we have capture-gated neutron spectroscopy that's available to us through some custom composite detectors. And the figures on this slide are kind of just a demonstration of, the operation mechanism and capability of those capture-gated detectors that we have. So just to conclude, what we've done so far is demonstrated production of nitrogen 16 and measurement of that 6.1 MeV gamma ray and validation against simulated models. We've proposed a novel nitrogen 17 calibration source that could be developed using the same delivery system. Nitrogen 17 calibration might be complementary to other neutron calibration sources such as americium and beryllium by providing different neutron energies and tagging systematics. And our models have shown that nitrogen 17 production from enriched water is feasible, and we're looking into moving forward with our proof of concept experiment to demonstrate it as a possible time-tagged neutron source. And with that, I will conclude by thanking our sponsors and opening it up to any questions. Thank you.
Wonderful, thanks Chris, it's a great presentation. We'll start with the question from the chat, which is about the result you show on slide 8. You show some experimental data there, and there's a fit curve. So we can see that the fit deviates from the data for the lowest times, which is the part of the plot where the statistics should be the best. So the question is, why does the fit deviate in that low time range?
Oh, in the low time range?
Mm-hmm.
So there's a couple different possible explanations for that, one of which is when you're in the very low time range, you're experiencing higher rates, so you can actually get a little bit of dead time losses that are happening. So that's one thing. There's also a little bit of just, die away from when the generator is turned off. So there's some rate issues that can be happening there.
Mm-hmm. So this fit, the red line, is a fit to these data points, or can you talk about that a little bit, how you arrived at this fit?
So the red line is not a fit. The red line is, well, it is a fit, but it's only fit using a scalar parameter, right? The decay constant, it's a simple exponential with a decay constant and a scalar, and the decay constant is defined as the known decay constant of nitrogen 16. So it's not actually a fit to the data. It's just been scaled to provide, the closest, I guess, fit that you could say. But the decay constant, the shape of that exponential, is not actually changed to model the data. This is just showing that the behavior that we actually witness is very close to what would be a perfect model.
Yeah, so you use the known decay constant of N16, and you scale it using the amplitude parameter to line it up.
Right.
Okay, makes sense. So question about splicing the data to improve the fit.
So what is the question?
Would splicing the data improve the fit? I think it means because you mentioned that when you during the presentation that this time decay was for a certain energy range. So what was the energy range, and would changing that range improve your fit or change your fit at all?
I think potentially, by narrowing the range, you could, basically, the wider the range is, the more you're going to have some sort of background events. You still get some high energy background events that can be happening from cosmogenic and muon background in the detector, things like that. So just by narrowing the range, you just increase the proportion of true counts to background. If we were to center it around something like the 6.1 MeV photo peak, for example, that might be one way to go forward and get it to match a little bit better. But I think this is mostly just kind of a preliminary demonstration that what we see is what we think we see. It's caused by what we think is causing it. And so as just kind of a first order validation check of the fact that we're looking at nitrogen 16 events, for real, then I think that's kind of the main idea there.
Yeah, that makes sense. Naive question from me about the Cherenkov detection mechanism. So in your first couple of slides there, when you were describing the mechanism, you mentioned that the positron will create the Cherenkov in the medium, and you said if it has enough energy. So can you comment on what that means? What's the energy threshold, the effective threshold of this mechanism?
So I don't know offhand exactly what the positron energy is that's required, but essentially there's a Cherenkov threshold in water, right? And the charged particle has to be moving fast enough that it's moving faster than the phase speed velocity of light in that medium in order to create the Cherenkov light. So there is an energy threshold below which even these charged particles, positrons and electrons from gamma rays will not produce Cherenkov light in the detector. You know, I just don't know offhand exactly what that number is, but I think it's on the order of, you know, a few hundred keV.
And how do we collect the Cherenkov light?
So the Cherenkov light, so this is based off of the design that's been proposed for Watchman, AIT, NE0. And so in this large water tank, there's a very large array of numerous PMTs that are around the water tank that then collect that Cherenkov light.
Other questions for Chris?
Yeah, one quick question. Great talk, Chris. How much nitrogen-16 and nitrogen-17 do you expect to produce from the oxygen-17 sample?
So from our oxygen-17 sample, which is on the order of like 2 grams, what we expect to produce with a 10 to the 8th 4 pi nominal flux DT neutron generator is on the order of 150 nuclei per second. And so with the short half-life of nitrogen-17 and nitrogen-16, it means that you saturate very quickly before your half-life losses start to, your decay losses start to balance out, you know, your production. And so the maximum population that I think we can achieve is somewhere like 800 to 900 nuclei of nitrogen-17, you know, before the population saturates. And so the idea for that measurement is to operate the neutron generator in a number of cycles where we would operate it for about 10 seconds, about 2 half-lives of nitrogen-17 to build up that population, measure the spectral response during the decay period, and then of about maybe 20 seconds. So you have 10 seconds on, 20 seconds off, and then cycle that procedure over and over and over, which will allow you to build up the statistics to measure the signal from nitrogen-16 or 17.
Okay, thanks.
Other questions for Chris? Okay.